So welcome, and I'm Matthew Chatrone. I am the Deputy Director for the University of California Observatories. And the University of California Observatories includes Lick Observatory, which is where I am observing this evening, even though I am observing from my home in Santa Cruz. And Evan, would you like to introduce yourself?
Yes, hello. My name's Evan. I'm a third year undergraduate at UC Santa Cruz, and I've been working with Matthew for the past year on some stellar chemical projects, and I'll be helping him observe throughout the night.
Excellent. Thank you. And so if you have questions as we go along, feel free to raise your hand or put them into the chat, and Jamika will take care of that. What I think we're going to do is I'm going to talk a little bit about the science behind what I'm doing today, and then we'll watch the sunset. And actually, we are watching the sunset. Let's see if I can share the right screen here. That one. We're watching the weather, which is all greens across the board. So it's calm winds, good humidity, low particle count, mostly low particle count. And then here we're seeing the sunset. So that looks pretty. And every direction we look, we see no clouds or clouds only on the distant horizon. So it looks to be a really excellent night tonight. We do have one surprise tonight, is that we have been asked if we would interrupt ourselves with a target of opportunity. So there is a supernova that was discovered um, this morning, I guess 12 hours ago, this morning, early in the morning. And they found it later in the morning looking at the data, and they're asking if we will take a spectrum of it. So we will interrupt the science we're doing, and I think what we'll do is have that be one of our last targets of the evening so that you can see us set up on a supernova. So that is not what I normally would be doing, but we're all collegial. We're all one big happy University of California family, and so we work together that way. So what I will do is uh, a little bit of background. So where did oh, my talk has disappeared. Um, Hang on, let me find it. It's, my desktop is full of communications information from the telescope, and there it is. And And here we go. Great. So I wanted to introduce you to your telescope tonight. And so this is the Shane telescope. It was the second largest in the world when it was built in 1959. The glass was built from a blank used to build the Palomar 5-meter blank. And so it was a test of the procedures for making a really enormous piece of glass, which ended up being the largest telescope in the world for many decades. And so this other piece of glass was purchased by the University of California a few years later and turned into another telescope. And so it's 3 meters across, and it weighs 145 tons. And of course, designed by engineers and maintained by technicians, and occasionally run with astronomers. So there's a fleet of people who all work together to make this science happen. We don't have any cameras in the dome, but we do have a little footage that we will show a little later to kind of look around the telescope. virtually. And but telescopes are like cars without motors. So you have to have some sort of detecting device on a telescope for it to really be functional. So so here is an image of the stars, but if we want to find out more about these stars, we really need to go dig a little deeper. And so that's what spectroscopy does. So here you can sort of see bright stars, faint stars, red stars, blue stars. But you don't really know that much about them. So from spectroscopy, that's what we're really going to gain information. So there's a picture of our star, and then we take light from that star and pass it through a prism or a grating or something that disperses the light into its colors, and then we can analyze that. So in more detail, there's our enormous telescope sitting on the surface of the Earth and looking at the star. And so if the world were exactly like an orange yellow marble up there, then we would get a spectrum that looked like a solid spectrum like that. And so then we really wouldn't gain all that much information. But stars are much more complicated than just solid marbles out in space. They actually have an atmosphere. And so it's that atmosphere that really gives us more information. So just like the Earth has an atmosphere, stars have an atmosphere. So when the light from the center of the star tries to make its way out, some of it reaches us unperturbed, and some of it reaches the atoms in that atmosphere and gets absorbed and then re-emitted. And so that causes the spectrum to fail in particular places. And the failure places are like fingerprints. So you don't have a perfectly smooth finger, like a perfectly smooth spectrum. You have little ridges. And so this is the little ridges caused by atoms in the atmosphere of the star. And so knowing those atoms in the laboratory, we can then turn that around into determining what the composition and the motion and the pressure and the temperature of the star is. Okay, and so some of the lines that you can see there, the sort of the one in the green is hydrogen, and some of the other lighter green ones are iron, and the one in the yellow there is caused by sodium. And so the same sodium that you can find in sodium pressure lights that you can see on some older city streets that haven't switched over to LEDs, those are the same sodium type of atoms that you'd find in the star, in the spectrum of a star. Okay, so from chemical abundances, we have a solid spectrum, but because of the atmosphere of the star, you get these dark bands, and those dark bands we call absorption lines, and that is the chemistry of the stars that we can see. So if you turn that spectrum on its side, you might look at it this way. And so here's a piece of a spectrum from the sun, and you can see different elements in there, iron and silicon and calcium, vanadium, barium. So those are all just different elements causing those atoms in the atmosphere of the sun, causing absorption. So the instrument we'll be using tonight is called the CAST dual spectrograph. And it was built in 1992, again, by engineers and maintained by technicians, and written by a bunch of software engineers who worked for the observatory. So again, it takes an army of people to make an instrument happen, and it's more than just astronomers. It's kind of complicated. There's actually two arms to the spectrograph. One arm works for the blue part of the spectrum, and another arm works for the red part of the spectrum. And you can sort of see there a picture of the fellow who designed it, standing next to his invention at the back side of the telescope. So it's about as big as a human. and weighs a lot more than a human, depending on the human. Okay, so and it's the research that I'm doing is based on a bunch of great astronomers you've probably never heard of. And so you can sort of look at their faces. This is they're listed in order here from Annie at the top to Cecilia at the bottom right. And you can look at them and say, why aren't these astronomers as well known as they should be? And perhaps it's probably because of their gender or their skin color, but they made huge contributions to astronomy and in the classification of stellar spectra. No one person did everything. Saha was mostly a theoretician, and so he took all the observational data and applied a lot of mathematics and physics to it and came up with an understanding of the temperature of stars. And the Cecilia Payne kind of put the whole system together as a classification of stars. And so I'm glossing over a lot of history, but this is what it boils down to, is that stars are classified in a bunch of color names, O, B, A, F, G, K, or O, B, a fine girl, kiss me. And the spectra look different between the O stars and the K stars. So each of these have different spectral features and relative intensities, and that's how they classify these stars. And they're kind of some of the things are labeled down here at the bottom, titanium oxide, so molecules. So let's look at this titanium oxide here. You can sort of see those are only found in the M stars. So that's sort of the descriptor of what an M star is. And then sodium, you can sort of see sodium. You can even see sodium in G-type stars, which is the sun. We saw that earlier, but you don't see it in A-type stars or B or O stars. Hydrogen is you can see in O stars and A stars, but these stars are too cool to really excite the hydrogen atom into losing into excited states. And so you don't really see hydrogen transitions in the cooler stars. So you use the fingerprints of the stars to kind of classify them into different categories. Was there something in the chat? Was a question, or was that?
It was something that I sent to
Oh, okay.
Evan, just that I'm gonna log out and log back in. Evan,
Okay.
you'll make me co-host again. Thank you.
Okay. So a summary, got the different spectral classes from very hot to very cool. And but there's something strange in that classification system. There's something called a carbon star. So in the spectra above, there are a bunch of spectra that are K spectra down to sort of M spectra. And then there's this oddball that really doesn't look like any of the others. So you can sort of see this spectral feature is sort of this spectral feature. So these are very common. Maybe they're stronger or weaker, but this spectral feature and this spectral feature, these are really unique. And so this is, they've determined that it was from a molecule called C2, that's a carbon plus a carbon atom. And it makes it stand out compared to all the others. So it got its own classification as a freak star. So we're going to take a quick aside about chemical evolution and why carbon stars are important. So from a person who works on the birth of the universe and in a theoretical sense, the Big Bang Theory, this is their periodic table. So when you were taking chemistry, wouldn't have this been a nice periodic table to have to remember? It's pretty straightforward. It's pretty easy. The Big Bang really only made hydrogen, helium, and a little bit of lithium. And that was it. And so where's everything else? Everything else is caused by stellar death. So in one form or another, all of those other elements are involved with the death of stars. And if we color code it, and so what do I mean by stellar death? So there's a couple of different ways stars can die. If you're kind of a smaller or a big star, start with the big stars. The high mass star, you become a red supergiant, and then you blow up, and you either become a neutron star or a black hole. And the cloud that comes out of that supernova produces a lot of elements. So that is one leg of the periodic table, comes from these type of stars, these supergiants, supermassive stars becoming supernova. But small stars also play a role. They can become red giants and puff off their upper atmosphere to become planetary nebulae. And that planetary nebulae slowly can drift off and join another cloud and form the next generation of stars. So it's low mass stars which become carbon stars. And so the carbon stars pollute the planetary nebulae, and then the core of the star becomes a white dwarf or a black dwarf. So this is what the periodic table looks like if you break it apart into what is the source of that, of the element. So again, hydrogen, all from the Big Bang. Helium, mostly all from the Big Bang, but inside of some stars you get hydrogen turning into helium. And so there is a little bit of production of helium in some stars. But then all of these other stars are produced by different types. So the yellow are low mass dying stars, or let's look at exploding massive stars first. So it produces things like oxygen, silicon, sodium, some iron, maybe only 40% of iron, but then all of like bromium and rubidium. And then low mass stars is the yellow. It produces like 60% of all the carbon and nitrogen in the universe come from smaller stars. It also produces things like yttrium and molybdenum, barium. Okay, so that's why we care about these carbon stars, is because most of the carbon around us today, the carbon in our DNA, the diamonds, the gemstones, all of that come from lower mass stars, not supernovae, but the smaller stars like carbon stars. And so traditionally, carbon stars were found with looking at spectra and looking for these freak big C2 bands. But then they determined, well, what really causes those is when there is more carbon than oxygen, because oxygen really loves carbon. So it loves to form carbon monoxide. And but if there is more carbon than there is oxygen, then there is excess carbon available after all the carbon monoxide is formed. And so you get a molecule called C2. And so it's really when there's more carbon than oxygen, then you get the C2 bands. But there are no C2 bands in the infrared. And there have been some really big surveys of chemical evolution based on infrared studies. And so they find stars that have more carbon than oxygen based on CO bands and CH and CN. And so they estimate how much carbon there is and how much oxygen there is. But nobody has followed up since then to say, well, if you go back to the optical, will you see those big C2 bands for those stars? So that's the survey that we're doing today, is confirming with a new survey whether you go back to your old-fashioned results in the optical, whether you would have classified the stars the same way. So that's your brief background of what we're doing tonight and why we're doing it. So I'll stop sharing here for a moment. Maybe we can take some questions, if there are any questions.
I don't see any questions in the chat at the moment, Matthew, but I am curious if you could give us, is there any particular reason why the C2 band doesn't appear in the infrared?
So each transition from a molecule has a particular wavelength that it falls in. And so there are CN features that are found in a lot of different areas. Heavy elements tend to only produce transitions that are in the ultraviolet part of the spectrum, a few that are in the red, but mostly all in the ultraviolet. So it's really just based on the electrons and their orbits around the molecule or around the atom. And C2 is kind of unique in that it has same mass, one carbon and another carbon. And so all the transitions are kind of very kind of high energy to make those electrons do anything interesting, because there's no difference between, if you had one side and another side, then you kind of get all sorts of strange modes, and you can produce like if it's a carbon and a nitrogen, they have different masses, and so you can get different modes and transitions all over the spectrum. But because C2 is exactly the same, one carbon and another carbon, it's very hard to excite it into a form that wants to emit, and so it only tends to emit in the optical and not so much in the infrared, not at low energy transition.
Got it. Thank you.
So one thing that I thought we would do here is take a little bit of a shared screen of, so here's our weather. We do have a little bit of dust creeping up, but nothing, I think, to worry about quite yet. But there's our sunset setting away, but we have this virtual tour, and maybe I can't really manipulate it very well from my vantage point. So maybe Evan, could you?
Which part do you want to see?
Why don't you just tour us around a little bit? So there's the back of the telescope, and let's see if I can tell. Yeah, the instrument is on there. So could you point out the instrument? Yeah.
Yes. So the CAS spectrograph is this kind of these black boxes that are attached to the bottom of the telescope. And so light's going to come down from the top up here, down past there's a little hole in our central mirror, which is in this tub, and it goes to all of our instruments down in here. And that's how we're going to observe the spectrum of these carbon stars. We can look around a little bit in the dome here. Our telescope has a nice protective dome that shields it from weather and rain and things. The opening for the dome is right here. This thing will move to the side once we're ready to open, and we can point it at the stars. Laying around here in the room, there are other instruments that we're not using tonight, but it's for other scientists. Here is the giant mount that our giant telescope sits on. We can spin this around and tilt it different ways, so we can point at all the different positions in the sky. Anything else you'd like to add, Matthew?
Is it possible to go to the other side of the room and look back?
Let's try.
Then you can see the fork mount a little better.
Yeah, here you go.
So that's about 10 feet across there, the back of that telescope. And the glass inside, of course, a little smaller. And when the glass was originally put in the telescope, it did not have that hole that Evan referred to. And so all the instruments were at other locations, up at the top of the telescope or down in the fork of the telescope. And so when they decided that they wanted to build a Cassegrain instrument, they had to take this perfectly good working telescope and drill a hole in the center of the mirror to allow the light to get down there. So they were quite terrified of this operation, but they were convinced that they could do it safely. So they took it out and drilled a little pit of a hole, and then slightly smaller, slightly bigger pit, and then a deeper, thin pit. And they just kept going to see, are we cracking anything? Are we making any errors? And then they finally made a small hole all the way through and then widened it to the size they needed. So let's see. At the moment, this is not a live image. This is just a Google tour that you can take. Are you trying to see where you can go? Can you go downstairs?
Oh, I hadn't tried.
I don't know if it will let you go downstairs.
Looks like I'm going in the room over here.
Oh, how funny.
You can see the top of the telescope up here.
That long projector that's black, that thing right there, that is part of the laser system, which we are not using tonight, but it's part of the adaptive optics system for the telescope. So it projects a laser out if we ever need an artificial star to help with our adaptive optics. Okay. Oops, yeah. Okay. Right now there is a tour in the dome of the telescope, and so our telescope operator. Oh no, we do have a telescope operator available. Will be telling us when the lights are off and when they're done in the dome floor. And when that happens, they will open the dome. I'll go ahead and stop sharing. Oh, I see a hand up.
Yes, Matthew. Okay, so we have a question. Okay, I think Rob may have also answered it for us. Thank you. So the question was, I'll share it to everyone, to you and Evan. What is the difference between nautical twilight and astronomical twilight? And do believe Rob has given us the answer, but please feel free to elaborate on that, Matthew and or Evan. Thank you, Rob.
I better look at the answer before I make myself look stupid. About 6 degrees. That's good. So when the sun is 12 degrees below the horizon, so about the distance of a fist held out like this, that's when you get nautical twilight. So that's where you can really stop really operations on a boat. You know, you can't start to see things in detail, and so it's no longer safe to do any kind of operations on deck because it's gotten too dark. So that's nautical twilight. And then astronomical twilight is about 18 degrees below. So that's a little more than your tip of your pinky to your thumb held at arm's length. That's about 15 degrees. So that when that's below the horizon, that's when the sky is finally dark enough that it's not really going to get much darker. And so it's pretty much as dark as it gets, except for, of course, the moon. So the difference is 12 degree and 18 degree.
Perfect. Thank you.
Okay. So tonight we have been asked for a little bit of an interrupt to look at a supernova. So a lot of our stars are carbon stars, which are those low mass stars which will eventually die to become things like planetary nebulae. But we're going to interrupt ourselves with another type of chemical evolution event, which is a supernova. And we don't know what type of supernova. We just know that this is in another galaxy, probably, and it has gotten a lot brighter than it was just a few days ago. And so this is coming from the 48-inch at Palomar Observatory. Takes pictures all over the sky every night of the same parts of the sky. And so each night they look at the same images and see if there's any new stars in the sky. And if they see a new star in the sky, then that might be a supernova. So we're trying to go in and take a spectrum to confirm to see if this is not another star in our galaxy, but another star in another galaxy that has gone and become an explosion. So it becomes as bright as, not quite as bright as the entire galaxy, but it rivals the galaxy's brightness altogether. So really becomes gigantic. Gigantically bright, not necessarily big. Okay, so we can watch the sunset a little bit and watch the weather. Whoops, did I share the wrong screen? Stop share. Try that again. Let me check in with our telescope operator and see how things are going. Oh, he walked off. So I've been up there 3 times or twice this week up at Lick Observatory. I was there last night, and I've been watching for a green flash and have not had a lot of luck. But maybe we will see some pretty colors as we get to the horizon. Sometimes the last little bit of light that peeks over the horizon. Whoops. Could we come back to that? Yeah. Oh, thank you. Can be dispersed, and the last colors to make it across are sort of the greenish or the bluish colors. So we get kind of a little green flash sometimes at the end if there's a very sharp horizon without too much fog over the Pacific. Jamaica.
Yes, thank you, Matthew. At first, that view of sunset is absolutely stunning, absolutely beautiful. And next, I just wanted to ask if you could share with the group while we're enjoying sunset, and hopefully maybe we'll catch a view of the green flash, what you were sharing before we started about the potential of seeing aurorae
All right.
all the way down to southern states tonight.
So lately we have had solar weather. So the sun is not a marble in space with a very thin atmosphere around it. It's actually a roiling, broiling um, ball of gas with a magnetic field and a lot of activity. And sometimes that activity gets ejected in giant flares. And so one of those flares recently occurred, and we may see its impact on the Earth tonight. And so when it hits the Earth's magnetic field, a lot of those free electrons and protons get transferred over to where the poles are. And so we end up with that exciting those free electrons flowing in and hitting the gas in the upper atmosphere and heating up or not igniting, but exciting the nitrogen gas and the oxygen molecules and different molecules and atoms causing different colors. So you can get some reds and some greens. And so the idea is that maybe tonight, because of this giant solar storm, ejecta, we might actually see some aurora here in Northern California. So we have an all-sky camera. Moment. Yes. So, but later, when the sun goes down, we will start to see some detail. And maybe we will see a hint of it off in the north. Jimmy?
So I have another question in the chat. Oh, and also I think this is Sunny said, yeah, that's so cool that your friends in Houston are reporting seeing the aurora. The aurora. I've never seen it personally myself, and in Hawaii, I know I'm not gonna get a chance to, but amazing that it's reaching this far down. And I love that it really highlights how active our sun is, goes through this 22-year cycle of, being active and then not so active. And I think this really allows people to learn more, encourages them to learn more about our wonderful sun. Okay, question from in the chat from Vonnie. This is regarding the supernovae you said we may see later this evening. How often do supernovae appear in our galaxy compared to other galaxies?
So our galaxy has one maybe once every, I think it's supposed to be once every 50 years, but it has been more than 50 years since we've seen a supernovae. So there was one in our little neighbor decades ago. That was only seen from the southern hemisphere. But in our galaxy, they don't seem to be occurring very often, and it may be because our galaxy is very quiet. It isn't forming stars really aggressively. And so when you have massive stars, you get, and lots of them, then you get more supernovae. So, but our galaxy a couple of galaxies we've seen in the last 15 years. So that would be a pretty spectacular or unlucky, if you were living there, galaxy to live in, to be in. So it would be spectacular in their night sky for a very short period of time. So there's our
Great, thank you.
Yeah, I think I see fog there on the horizon, and it's a band there. Let's see, sorry. But so somebody was reporting that they had a friend in Houston who was seeing it. Is that correct?
Yes, we have here in the chat, this is Sunny. I believe that was Sunny said that let me lower my hand. The Sunny said he had friends in Houston reporting that they've seen it. How far south will we normally, without this extra amazing solar weather happening right now, how far south would the Northern Lights typically go?
So I lived in McDonnell Observatory, which is in Texas near El Paso, or maybe not near, but 200 miles into the nowhere land of Texas in the mountains. And in 23 years of living there, that far south, I only saw it twice. So, and once was kind of just a faint, couldn't tell if it was a white cloud that was there, but I knew it was supposed to be happening, and there didn't seem to be any clouds on the radar. So I thought maybe that's probably it. And then one time it kind of had a red color. So it's not very common, maybe once goes through sort of decadal in length periods of time where it's active and inactive. And so we are at height of activity. So we may see a couple over the next year where it gets down this far before we go into a quiet period again. So wow, that sun just doesn't seem to want to go down below the horizon, just hanging out there. Oh, okay, we got an update. It's not, I guess it takes a frame and then waits and takes another frame. So that's what we're waiting for. Okay, so now the sun is below the horizon. Hold on, are you there? Matt, are you there? No. So they're probably trying to shoo our tour group away, which apparently are some of Evan's classmates. So Evan, you want to tell them about what the class might be doing?
Yes. So, as a part of the astrophysics undergraduate degree, there's a lab class for astronomy, and the class gets to go up, I believe, 3 times in 1 quarter, and they get to observe on the nickel and the Shane as part of their lab class. And they'll do a few different projects. They'll do spectroscopy, like what we're doing tonight with the cast. They'll do photoimetry, which is looking at the brightness of stars and galaxies. And they'll use the nickel for that, which is a slightly smaller telescope, but still on the same observatory as the telescope we're using tonight. and you write a lab report on what you observe and things, and you turn it in for a grade. It's a pretty cool class.
And Evan, would you tell everyone how you got interested in astronomy?
Yes. I'm sure many people in the Zoom can share the sentiment of always being interested in the night sky. As a kid, I had visited observatories and gone stargazing when I go camping. But coming to Santa Cruz, being a research university, I got involved with astronomy research with Matthew. And for the past few years, I've been doing research on stellar chemistry in conjunction with my normal schooling. And it's been a great time.
Thank you.
Yeah.
So, so I said where I was observing from. So it's possible to observe from the telescope, and but it is also possible. We had dedicated communication lines to each of the campuses, and we set up control rooms. And so Evan is in one of those control rooms on the UCSC campus.
Yes.
And it is freezing cold computer room in there. So
Not so bad, but the school computers are just behind that window there, and they have to keep it chilly for the computers to run properly. And there's not much insulation between me and the freezing cold computer room.
And then during at the beginning of the pandemic, we sort of had to shut down campus. So you weren't allowed to go up to campus, and we weren't allowed to go up to Lick Observatory except for those people who already lived on site. And so we limited the number of people in the dome and the control room to just one person every night. And so in order for the astronomers to be able to operate, we came up with what we call pajama mode, which is the ability to observe from your own home, from the safety of your own home during the pandemic. And it has been so popular that people like to be able to observe from their couch and control the telescope. So, we have some activities. So I'm going to stop sharing and go back to the telescope operator is getting the telescope focused. Hello. So good. I have a Shadow the Scientist group here, and so I'm narrating a lot. So feel free to tell me when and interrupt me, please, when you're ready for something. So the what you're seeing is an image of a fairly bright star that they can try to focus the telescope on. And let's see if I can zoom in a little bit. And you can sort of see it wobbles around, it kind of flickers, it changes shape. That's the intrinsic atmosphere distorting the image. And so some of that, if it's well out of focus, it will have, that's what it looks like. And then when it goes into better focus, it'll be kind of a sharp thing that kind of wanders around. And with adaptive optics, you can get rid of a lot of that wander, skipping, amoeba shape generation and lock it down to a much smaller size. So I don't know if you can hear, but the telescope operator just told me that the seeing was 1 arc second in size. So that's a very good number. So we're in for a treat, a good night tonight. And are you ready for a target?
Yes, you can send one over.
Okay.
It's still a little bright outside.
It is a little bright, so I'm going to send a standard and we can just take it. It's pretty bright.
Okay, good. Cool.
Okay, so
Solar telescope at the main building, so with the little black spots. Solar flares. There's a couple black spots. I think, spots and solar flares. Pretty neat. I scared really hard.
so they were reporting from at the main building with some of the tourists that they have a solar telescope set up, and they're able to see some activity on the surface of the sun, some star spots and such. Okay, so let's see. Send a target across.
Target?
I have sent you a target and we are ready to go.
Do you have a PA for it?
Oh, yes, I do. 200, please.
Okay, thank you.
So the instrument on the bottom of the telescope has the ability to rotate so that there is a long slit that separates out, isolates the thing that you're trying to take a spectrum of. And it's quite long and narrow. And so you can decide how you want to place it on the sky. And so we are trying to place it at an angle such that the most light can go through, even if some of it is diffracted by our atmosphere. So we have, this is what the object should look like, which is a little bit boring, but it's a bright star. And then there's a little bright star here off to the southwest. Let's see if we find the star. It's still very bright out. It's so bright that the camera is picking up. It makes it look orange. It's very, very bright still. Jamika.
Yes, okay, I got a direct message question. What is, sorry, let me just go back and read it. What is involved in starting the process of observing every night?
Right. So once you write a proposal and they grant you telescope time, then you show up at the telescope or wherever you're going to do the observing, and the instrument has to be configured because they may have taken it apart and put it back together. So you have to calibrate it, and these have detectors in them. And you can sort of see in this is only a guide camera, but it's sort of the same thing. You can see all these flaws in the detector or in the optics between the detector and the object. And so we can calibrate that by putting on a bright lamp and taking some images that should be featureless. And then we can take that featureless spectrum or image and divide it into the image we're seeing and make a nice clean image. So that's one of the types of calibrations we use. We call that flat fielding. Another is that the instrument has motion in it, has motors, and so we don't know exactly where the fingerprint of the spectrum of the star will fall. And so we put in there some gas cylinders, which we heat up with electricity, and that emit its own fingerprint. And so we get a spectrum of a laboratory source, and then we can use that to calibrate where we would expect the velocity of a star, or a spectrum of a star, to appear if there was no velocity of that star. If the star does have velocity, then it might be blue shifted or red shifted compared to that laboratory reference frame. So those are the two big types of calibrations that we do: flat fielding and wavelength calibration, or a calibration for velocity. And that takes, I guess, an hour for every setup for us. And so we had two setups tonight. One, the normal one we're doing for the research we're interested in. And then the request for doing the supernova means that we have one other calibrate. They want a slightly different setup than the one we're using. We are interested in very high details of these carbon stars to look for those C2 bands, and maybe they might be weak. And so we want to make sure we look in great detail. The people interested in the exploding star in another galaxy, they're not looking in that great detail. They just want to know, is this an exploding star, or have we been fooled? Or what type of exploding star is it? And there are different types of exploding stars. There's ones caused by massive stars, one caused by binary systems. And then sometimes those binary systems, whether they have hydrogen in their atmosphere or whether they're old and have eaten up all their hydrogen. So they can learn something about the progenitor of this explosion by looking at the spectrum, but they don't have to look at it in as great detail as we are. So they can use a more general purpose, lower resolution, we would say. And there's our star. There we go. So there's the long slit that goes from left to right. And they're going to place it on that slit. And so suddenly, instead of having a reflection, it looks like the thing is being cut in half. But really, the spectrograph is behind that slit. And so if it were a perfect night, all the light would disappear down that little hole, or not hole, the long hole, the slit. And so Evan, would you mind setting up I guess I can send to Poco. Send object name, there we go. And let's do 20 seconds on both.
All right.
We'll see what that looks like. So I will stop sharing there and show you a little bit of what Evan is doing.
Should I start exposing?
Not quite yet. We haven't gotten the green light from the telescope operator.
Hey, we're guiding.
Okay, that's the cue. So they're ready, and so Evan is going to push. Good catch.
Do you want to change the observation number at all?
No, I think it's fine.
Okay. So I'm going to click this button here, start
Mhm.
exposing, and the camera's going to turn on, and it's going to collect the starlight.
So we.
Oh, go ahead.
Go ahead, Evan.
Well, I'll just say when I click the start, you'll hear these dings and chimes, and that's coming from our computer. It's a system put in place to keep astronomers awake when it gets to the late hours of the night, and you can't remember what you clicked. So you have the voice memos going so you know what step you are on. So we just finished exposing, and now the computer is going to read out the image that we just took.
Okay, so here's the top is the blue part of the spectrum here. And so the star is here. This back here is the sky. And you can sort of see the sky is still very bright. And but you can sort of see all these little not black holes, that's probably the wrong word to use with this crowd. These little black marks on the detector. And that is flaws in the optics and in the detector. And so we can calibrate that out with our flat fielding so that they make almost no difference. But we can sort of see a spectrum here. And Evan, if you'll do a cut across there, we'll see what the signal looks like. And the peak is about 5,000, and the background is the background level is 1,800. So we can probably go to 60 seconds.
On both sides?
Yeah, on both sides. Just do one more 60-second, and then we'll switch over to the supernova setup.
All right.
Okay, so I don't know if this is too zoomed out because you're seeing everything kind of happening all at once. We've got one screen that has the red detector in it, and another screen that has the blue, and another screen is the guider information. And another screen, we watch the weather. Speaking of which, we can go to okay. Check one more time, see what it looks like.
We're at 6,000.
Okay.
And
2,000 is the background. That's good. That's probably good enough, in fact.
all right.
And do you want to do, you did a row cut, which was kind of interesting looking. Can you put it right in there and do another row cut? About just a little bit more, maybe. Yeah. So that's what the spectrum of this star looks like. And so I can see hydrogen. This is a calcium feature, this one here and this one here. And this is a hydrogen feature, so that I see reasonably strong hydrogen features, which tells me that this is probably like an A star. And the calcium are still there, so I know it's not an O star or a B star. So that's spectral classification from old school way. Evan, do you want to switch over to the other configuration?
All right.
It's hiding behind the spectrum there on the red.
Found it.
Yep. And you can just, yep, that's the one.
So this window here controls all of the different gizmos in the telescope. And so we change how the telescope is set up depending on what kind of science we want to do.
Okay. All right. So this might be too bright, but we'll try 60 seconds. Once it's done moving. Still moving things. And if you look over on the guider, the slit is now a little wider than it was before. And that's because they want as many photons as they can get for this very distant exploding star, which is 10,000 times fainter than any of the objects that I'm going to be observing tonight. Okay. I think this is a good name to keep on there. And so let's try taking an exposure.
All right, 60 seconds again.
Yeah.
So Matthew, do you want to explain what the importance of having a red and blue side is?
So the more you spread out the rainbow, the higher detail that you can see in the fingerprint of the spectrum. And at some point, you get it to be so spread out that you don't have a detector that is long enough to be able to spread out the spectrum more. Most of the detectors you buy, like you would put in a camera, are kind of square. And so they're only as long as they are as long. And so in order to have a second one, you have to sort of split the light and put it someplace else and put another detector over here. And so that's the idea, is that we have can spread out the light as much as we can by putting it on two detectors. Okay, let's see if we saturated anywhere. Got too many photons. Try there. Let's see. Look at that. Oh, come forward. Well, that's not too bad. So how about down here on the red chip? A little higher up in the area that's super bright there. Yeah, let's see what we get. That's too much.
All right.
So let's do 20 seconds.
20 seconds.
And we can leave the 60-second alone, I think, just to one of each.
Okay. So this is cool. Down here in the bottom right, we can see this is the telescope that we're using tonight, that we're controlling remotely. And you can see that the dome has opened. So that little black spot, it's, the shutter, the dome wall has folded back, and our telescope is hiding in there and looking at the stars.
Looks like an Ansel Adams image.
It does.
Okay, let's check our red one again. Make sure it's not in a bad way. That's okay. Less than 30. Check a little higher up. Great. It looks good.
Okay.
Okay. So I think that calibrator is good. We can probably go to the next calibrator and see 152. So I've set another target and we are ready to go at 153.
So up here on the top right, we can see the guider camera start to change a little bit as our telescope operator slews us across the sky, point in a different direction, so we can see our next calibration star.
Yeah, so we'll take two calibrators and then see what if we can go off to a maybe one carbon star and then go look at the supernova.
Sounds good.
We have to let the sky get a little bit darker before we can do that. Here's the chart for our object.
Looks like we have a question.
Go ahead.
Yes, thank you. So the question is, how do you determine if a star, if the carbon in a star is the same as the carbon in our DNA or in gemstones? And that kind of goes back to the session description that you used.
Right, that is a very good question. So I can't tell you if any particular atom links back to a particular event in the past, but it's what they do is they look at stars that are currently in the process of exploding or that are in the process of becoming a planetary nebula, and they look at the output and see how much carbon is there, and then they infer with models how much carbon from the sun is probably, and the Earth is from one type of explosion versus another type of explosion. You can tell a little bit by the amounts of carbon 13 and carbon 12, or magnesium 24 and magnesium 25 and magnesium 26. Sometimes you can tell from the isotopes, but carbon's a really tricky one because life changes the carbon on the surface of the Earth. So you kind of have to go and find rocks that have never touched life in order to understand what the primordial cloud that the Earth formed out of, what ratios of carbon 12, carbon 13, even carbon 14 even are there in that primordial cloud, primordial rocks. Let's see if are you able to identify which star is which, control room?
Almost there.
Okay, good. Take your time. So we have a new employee who's a new telescope operator training. And so they're learning how to identify. So there's a finding chart where north is up and east is to the, oh gosh, I get this wrong. East is to the left. And so the brightest one is sort of here. And so I think it is the eastern one. It's likely to be that one. I don't know. Pattern recognition is a tough thing. Let's see. So this guy there's a line, not quite east-west between those two bright ones. So that's probably this one, and he's a little south of that, and he was a little over and down. So
Right now, the wording shutter position for the right now.
so
Shutter, or the opening to the dome. North. Okay, so, but it's also a little bit west, right? Yeah. And where's the sun setting? In the west.
So one of the things you have to do is make sure you're on the right star. And once in a while, I'll take a spectrum and look at it and go, gee, that really doesn't look like a carbon star. And I was pretty sure this was going to be. And so I'll go back and look and say, did we, it's 3 o'clock in the morning. Did we accidentally observe the wrong star? And so we can look at the finding chart and go, oh, yep, there it was. There was the pattern that was a little bit can fool you, and you grab the wrong star sometimes. So it's always tricky. You have to stay alert even at odd times of the night. Let's see, how are we doing on the all sky camera is still a little bit all saturated. Okay, so I have to Evan, this target is fainter, quite a bit fainter.
Okay.
So why don't we do 1, 2, why don't we do 4 times longer?
4 times than what it is now.
Yeah.
So I'm going to do 80 on red
Uh-huh.
and 240 on blue.
Sure. And then maybe we'll take a couple of red
Okay.
exposures.
Are we ready to expose?
Nope, we haven't heard from, I haven't heard from them saying they're ready, but I turned down the volume also. Jamika, go ahead.
Thank you. There was just a question about where we can find some of your work, some of your most recent published data, or like a paper or something. Do you have a link you could share with us?
Sure, I could try to find something that's handy. Let's see. So let's, oh. So Evan, did you hear that? That they're done, they're ready to guide and ready to expose.
I did not. I have their volume down.
Okay, so yes, we're ready to start. So why don't you do 3 exposures there and 1 exposure on the blue.
All right. 3.
I've put through into the chat uh, a link to one of my most recent papers that's I'm not first author on, but rather a student of a colleague of mine is building on one of my papers. And so it's a sort of very recent paper that just came out. And but I do a lot of teaching now, or not teaching, but mentoring, I guess. And so a lot of my papers, I am not necessarily the first author on. And but I do a lot of different types of science too. And so that's one type where I'm looking at the detailed chemical compositions. And this is a different type of science where I'm looking at a globular cluster around the Andromeda galaxy and trying to, this is a gigantic globular cluster bigger than Omega Cen in our galaxy. And it holds mysteries that we are trying to disentangle. There is some thought that maybe it's not even a globular cluster, maybe it's the core of a little dwarf galaxy that's been stripped apart. And then the other last type, I will put a third one on there. I think this is, did I type it correctly? No. Copy. And here's the last one, and this is looking at the history of research at Lick Observatory. So I do a little bit of analysis of historical trends and trying to predict how things go into the future. You know, how publications come out from the observatory and what hot topics are and what the trends are. Okay, so we are just about 1 minute away. So I better, oh, we're going to switch over to, can you check the intensity to see if we saturated anything? Is it saturated? Whoop. Turn again. Nope. Okay, how about on the red? Okay, that looks good. You're welcome. Okay, so when this one is done, Evan, can you switch us over to the other setup, the carbon star setup? And when he does that, we can watch over on the area here to see if as the slit gets narrower as the components move. And whoop, it gets a little bit more narrow. So now you see more light peeking out the edges. Okay. And why don't we just do 240 in each? And that's good. So we can just hit start. once it's done moving, sorry. So, okay, I think it's all done moving, isn't it? Great. Load in our target file. And all the easy ones. We have a target list that I'm looking at over by the guider, and they have different categorized names. And this is the last night of this program. And so I've had probably not quite a dozen nights over the last 2 years to do this project. And so I've done all of the easiest ones, and what are left are ones that are of dubious quality or are quite a bit fainter and take a little longer. So that's a good one. It's bright. Okay, just 1 minute left, and then we'll head on to this next target. Okay, ready to move? Okay. Parallactic angle 179. So you can sort of see the star just whipped away as he moves the telescope. It was sitting in here and zoom, went on out. Chart. Should be pretty obvious. Okay, Evan, would you set it up for 220-second exposures? I've been
Sorry,
observing
Matthew, when you say two, do you mean 200 or two exposures?
2 exposures of 120 each.
Okay, gotcha.
So we'll use the I get command for both of them with a 2 in there. Perfect. So I've been doing most all instruments in astronomy, professional instruments, they all count up in seconds. And so, I know that 360, 3,600 seconds is an hour, and 1,800 is, 30 minutes, and 2,700 is 45 minutes. And, so my brain just works in seconds. And so when I go and want to microwave something, I'll put in, I want to microwave it for 90 seconds. My wife always looks at me like, you're so strange. Why don't you put it for a minute and a half? And I'm like, well, I don't know. I don't think 1, 3, 0. It's just 90 seconds. Hey, they're guiding Evan.
All right.
So the sounds that we're getting from these tend to be the least offensive sounds that still can wake you up in the middle of the night. And there are other sounds that one could choose. And as with many things, it gets developed at smaller telescopes and then implemented at larger ones. And so the final products and the nice modern sounding things will often be found at like the Keck telescope, which is our big sister telescope. And so, for example, we experimented with voices, and this was the voice that we ended up with.
Readout complete.
Which sounds a little bit digital and a little bit strange, but the one they have at Keck it's a woman's voice. It's a little more pleasant. It's it just comes off nicer. But here's the original Joel.
So was the guy's name Joel who recorded it?
Yeah. Is there one more in there? I can't remember if there's one more. And of course, big Star Trek fans, as usual for astronomy, and so you can find lots of sounds stolen from science fiction stories. Huh? Go ahead, Jamika.
Thanks, Matthew. Okay, we have another question in the chat. What is the ID, the ID number of the supernova you were observing earlier?
Well, we will be observing a supernova coming up.
Yes.
The one coming up, its name is what is its name? Let's see. Let me see if I can find it in my mail. I have it loaded in my coordinate system, so I can't quite reach it at the moment. Let me just the name is blocked out on the. Oh, here it is. 2024 INV. Indigo Nancy Victor. So it's not a very exciting number, but that tells you what year it was discovered, and they would have a running number by 3 letters that indicate when it was discovered or what order it was discovered in. And let me see if I can find out from telescope operators if we are in 18 degree. So, Jeff, do you know when 18 degree is? Do you know when 18 degree? Have we reached 18 degree yet? So we have hit 8. 2009. Okay, so we have a little bit to go. Okay. All right, so should pick out another target before we go to the supernova. Maybe 2 more. So they have sent you a new target and a deck of 10. We're ready to go. The parallactic angle is 189. So we still have roughly 30 minutes to 18 degree twilight. So we're probably at nautical twilight now. San Jose is looking very pretty tonight. It's even prettier when the fog rolls in and it disappears completely, because then the sky gets darker. Okay, so looking here, I see a Big Dipper. So I suppose that means north is up here. So as we get dark, I guess we need to look at the top of this image to see if we see any indication of kind of a light area up there. The top of the image. That panoramic doesn't go down very far, but I don't know if any of our other cameras point north. Um, oh, so could we do two 264-second exposures? All right, ready to start. Evan?
All right. You want two?
Yes. Okay, so let's see, what are our webcam options here? So towards San Jose, that's going to be either west or north. This direction is main building towards the Shane, and I think that is probably the Sierra Nevadas out there. So this is sort of east. Oh, this is a different all sky. Okay, I find the Milky Way here. Not the Milky Way. If I can find the Big Dipper here. Why can't I find the Big Dipper here? Not an amateur astronomer. And I can't find the Big Dipper. That's very sad. Evan, do you see the Big Dipper?
I do not.
Somebody stole the Big Dipper.
Is it that one on the right there? Like
Uh,
these guys here? I don't know. I might be
No,
kind of pushing it.
that doesn't look right, and it doesn't point the right direction. So, um, that's odd. So I'm assuming the bright area here must be west, right? That's where the sun set.
Right.
So west and east and Well, if that's west, then this must be north, right? Right? No, that's south. So it's funny whether you're looking up or looking down. I always get it backwards. So if I'm looking up, and west is over on my right, then south is
I think north is down.
put it. So that must be the moon
Hmm.
setting. Is that Cassiopeia? It's one exposure, one to get, one down, one to go. And maybe this other image is old and the Big Dipper isn't even up right now. Wouldn't that be funny? Yeah, maybe I don't see them. Maybe that wasn't the Big Dipper that I was pointing at earlier. That's not the Big Dipper. I don't know what it was. Okay, so stick to what you know. How about we take spectra?
Good thing you're not driving a boat.
Right, right, exactly. It's a skill set to be able to identify and find your way around the sky. Okay, so in 3 minutes, we're going to be ready. And we are not quite ready to go to we'll do one last object and then we'll go do the supernova to
Sounds good.
cap the night. Well, actually, I guess you guys were only expecting to do 2 hours, so maybe we'll go do the supernova next. I don't want anybody to have to run off and miss it, so maybe we should do that. So the next object is going to be our supernova. And take control room. Yep, can you hear me? Our next object is going to be the supernova. And so you should have the chart in the notes for the night. We're still a minute away from going, but I just wanted to make sure you were ready. Correct, that is correct. We have 25 more seconds. So let's see if I can. We are ready to go. And the angle is going to be 193. And I'm going to stop sharing for a moment so I can share the finding chart. Or the discovery image, I guess, is what they're using. So this is the discovery image. So there are a few stars marked, S1, S2, S3. Those are not the supernova. The supernova would be right there. Sorry. Okay. Communications didn't go through. So so they have offsets potentially for from the star to the object. So this is probably an image that is not the discovery image, but rather an image of before. So we'll see what it looks like. Stop sharing. Go back to the guided image. So supernova easy, X marks the spot. So it should be the object towards the south of the galaxy. So this object is probably this object. This bright one, it's this one. And this little thing is probably where the supernova is, right there. So it's that little guy right there is the supernova. So he is almost as bright as the galaxy, but not quite. But he was just one big star that had indigestion.
And just to be
Oh,
clear,
we need to change the setup, Evan. Could
Yeah.
you change to the that'll make the slit bigger. And do you have the email where they said what the exposure time they wanted was?
I believe it's buried here.
I think they were saying 4 10-minute exposures in the red and 2 20.5 in the blue. So 12:30 in the
12:30. And you want how
In
many
the-
of those?
no, that's in the red, it should be 600. And there'll be 4 of them. Okay, and in the blue, it'll be 12:30.
And how many blue?
2. And he said he's guiding, he's ready to go.
All right, start exposing. Right name. Pure.
You not do the get blue?
I
Two?
clicked expose. I'll just click it again once it
Okay. Got it.
Yeah.
So that is our supernova. Almost like doing another star, except for the fact that it's in another galaxy. Oops. So I want to thank you all for being troopers and putting up with my antics. Oh, what is the name of the galaxy? That's a good question. So it doesn't have a name, I don't think. It has a phone number. Let's see if I can find the NGC. Where is it? Well, I don't see it, the name handy now anymore. I looked it up earlier, but now I don't see it. See if I can look it up, see if it'll say. NGC 3524. So I'll put that in the chat. Oh, lost my window. GC 3524. Thank you. So, something we can say. This is not my field of study. We look it up on Wikipedia. It comes out in Russian. It's interesting. I think I'm on the wrong Wikipedia. Wow. Sure how that happened. The lenticular galaxy in Leo. Looking to see if it would tell me a distance. But I don't see a distance. Okay, well, anyway, thank you everyone for joining in.